Welcome all. Now we are discussing theorem 3.4 Baire's theorem. Let X be a metric space, then the intersection of finite number of dense open subsets is dense in X, and if X is complete, then countable intersection of open dense subsets is dense in X. Okay, let choose some collection of open dense subsets D1, D2, D3, etc. Now consider an arbitrary open ball U0 with the center x0 and some radius r0 positive in X. So we know that every dense subsets will intersect every open ball in that set X. Okay. Now D1 is dense, that means D1 intersection U0 is not empty. Then we can choose an element x1 from D1 intersection U0. Since D1 intersection U0 is open in X, since D1 is open and U0 is open, there exists an open ball called U1 with the center x1 and radius some r1 contained in D1 intersection U0. So that is x1 is an element of U1, that is a subset of D1 intersection U0. Okay, now consider D2. D2 is dense in X, and so D2 intersection this U1 is not empty, and similarly we can choose another element x2 from D2 intersection U1, and since D2 intersection U1 is open, there is an open ball U2 with center x2 and radius r2 contained in D2 intersection U1. Continuing this, we get x3, x4 follows. Similarly D3 dense in X, and so D3 intersection U2 is not empty. We can choose x3 from D3 intersection U2, that is x3 is an element of U3 and that is a subset of D3 intersection U2. Continuing like this, we obtain a sequence x1, x2, x3 in X and some positive numbers r1, r2, etc. such that xm is an element of um, where um is an open ball with center xm and radius rm contained in dm intersection um-1 for m equal to 1, 2, 3, etc. Okay, note that each um is a subset of um-1, subset of um-2, etc. Subset of u1, subset of u0 for all m. Okay, now consider for a fixed n, xn is an element of un, that is a subset of dn intersection un-1, we know. That means xn element of dn and xn element of un-1, but un-1 is a subset of dn-1 intersection un-2. This means xn is an element of dn, dn-1, dn-2 and so on. That means xn is an element of intersection m running from 1 to n dm. And also we know that xn is an element of u0. So xn is an element of intersection dm where m running from 1 to n intersection u0. That means u0 intersection, that finite intersection, is not empty. This means that finite intersection of open dense subsets intersects every open ball. That means intersection dm, m running from 1 to n, is dense in X. Now we consider the space is complete. So if necessary, we assume that the radius rm is less than or equal to 1 by m and um closure is a subset of dm intersection um-1 for all m equal to 1, 2, 3, etc. Now consider for n comma j greater than or equal to m, we have xn, xj element of um. We know that is true by our construction. So now consider d of xn, xj by triangle inequality, we get that is less than or equal to 2 by m for all n comma j greater than or equal to m. This inequality means that sequence xn is a Cauchy sequence in X, and so since X is complete, this Cauchy sequence converges in capital X to some point X. Okay, so also we know that xn is an element of um for all n greater than or equal to m, and so the limit point X is an element of closure, and so we get X is an element of closure, subset of dm intersection um-1, that is a subset of dm intersection u0, implies X is an element of intersection dm, m running from 1 to infinity with intersection u0, and this means that countable intersection of open dense subsets is again open in dense in X.